Okay, guys, it is Monday, May 11th, 2020. Top left corner of my paper, 5/11/20. Again, Monday, May 11th. The title at the top of my sheet here is Library of Functions. I'll explain that in a second. This blank sheet that you are looking at right now is attached to Schoology under the date 5/11. So my first piece of advice is to go to Schoology. You can pause this video if you need to, because I want you to go to Schoology if you haven't done this yet and print out the document that's attached with today's date, 5/11. And if you can print that out, you will then have a blank copy of these functions that we're about to sketch together that'll serve as our library of functions or as our reference sheet to use as we move forward then the next couple of weeks. So again, guys, if you could print out a copy of this sheet that is on your screen right now, have it in front of you ready to go. And if you can't do that or don't want to do that and would rather just sketch each one on a piece of notebook paper, I guess you can do that if you don't have a printer available to print this blank sheet out before we get started. Okay, it's your call. Now, what we're going to do, again, I'm talking, by the way, now to all juniors in mods 2, 3, and 4, and the 4 juniors, so Abigail, Bryce, Erica, and Isaac, that are left in mod 7. We're all kind of in this together now as advanced math or trig students for the rest of the year, for the next 2 weeks, and we will all be learning the sketching of the functions that I'm about to describe today. So this is for all advanced math trig students, mods 2, 3, 4, and 7. Okay? All right, if this is printed out and ready to go, I do have a note at the top of this. It says, note, a skilled calculus student, or I could say a skilled advanced math student at this point with you guys, will use his or her perceptions of the following functions to assist him or her on a regular basis. Now, my translation into English is, guys, starting right now, you must know these functions well. You've got to be able to look at any one of these 18 functions that are on this library of functions, and you should be able to do a quick sketch just on recognition alone and seeing what type of function it is. If we were in a real classroom setting right now and I was in front of you guys, I would hand this out to you and I'd say, okay, here's my stopwatch. You got 10 minutes, ready, set, go, without a calculator. See if you can sketch all 17 or 18 of these functions and tell me a general shape of exactly what they look like as we move forward into next year, as hopefully most of you will be a calculus student or a pre-calc college credit plus, or at some point moving forward to a higher level of math than where we're at now. My point is, you will never ever be taught how to graph any of these again. You are expected to go into your next higher level of math already knowing how to sketch these, because as I introduced you to calculus next week, Mrs. Moser's going to throw a function on the board. Let's say it's y equals 2x squared plus 5x plus 8. And she's going to say, what's the slope of that function at x equals 7? Or find the area between that function and the... You've got to be able to take that function and quickly sketch the graph of it just to visualize the question you're going to be asked at that higher level. You're not going to spend days reviewing how to graph functions. It's already expected you know it. So, with that goal in mind, I'm going to fly through this real quick. This is supposed to be a mental type of day. We're not going to touch a calculator one time. In fact, the functions we're going to graph the next 2 weeks, as we get more specific than today, you will not be using a calculator. It's a mental, logical approach that's going to consistently work in terms of you creating a function as quick as you can. So here we go. Let's see if together you can think with me, have pencil or pen in hand, and our goal is to make, as quick as we can, a sketch of all 17 or 18 of these functions, and then use this as our library of functions, our reference paper, as we move forward into more specifics the rest of the week and into next week, okay? All right, here we go. Y equals, and it says C, it's some constant. So if I said, quick, sketch a function right there, what would that look like if it's y equals and then there was some constant sitting there? Now, when I say a constant, it's any number you think of. So let's just pick a number in our brain for the sake of sketching this as quick as we can. Let's say this said y equals 3. Do you agree that a constant function is just a linear function? It's going to be a horizontal line. So I'm going to go up in my mind. I'm just imagining going up 3, putting a dot, and draw a horizontal line right through there. So everybody agrees that a constant function is a horizontal line going straight across our paper. Go to the block number 2. Now it says f of x equals x. Of course, f of x is always what? Just the letter y. They're interchangeable, right? It doesn't matter if I have y equals or f of x equals. They both mean the same thing. They're representing a function, right? So y equals x. Oh, so that's really just 1x plus 0. My point is, the point of this lesson is what? If y equals, and you ever see an x to the first power, that's called a linear function. That's going to be a line, an mx plus b, so to speak, that's either going uphill if it's got a positive slope or downhill if it's a negative slope. Since this is just bare-boned basic functions and it just says y equals x, that is a positive slope going right through the origin that crosses through the x and y-axis at the origin, looking like that. Everybody agreed? That's the old function y equals x. If that would have said y equals negative x, it would have slanted downhill instead of uphill. How about y equals x squared? Again, notice, bare-boned, basic, good old x squared. Remember, that was called your parent function. Do you agree that's called a quadratic function and is simply what? The old smiley face centered on the origin. So my point is, next year in calculus, any function that's got a positive x squared in it, it might be 3x squared minus 7x plus 12, but you know it's a quadratic and is going to be a parabola that looks like a smiley face. If that was negative x squared, we're picturing frowny face. Right now, our goal is, can we skim through and do a general sketch of every kind of function you've ever been taught to graph? Now, if that was x squared, the next one would be x cubed. What would that look like? Now, careful, you're probably picturing a roller coaster that goes uphill, then downhill, then back uphill again and touches the x-axis 3 times. You're correct if that would have said x cubed plus 5x squared minus 7x plus 4. Again, this is just the bare-boned, good old x cubed function. So if I thought about this for a minute, what if I made an xy table and you plugged in the numbers -2, 0, and 2? What's -2 to the third power? Wouldn't that be -8? Right? So I'd go left 2 and down 8. Plugged in 0, I'd get 0. Right 2 and up. Oh, guys, we're picturing a curve that's very steep that ends up looking like that for this particular sketch of the function y equals x to the third. It's steeper, squiggly line that looks like that. Agreed? All right, the fifth one. Y equals, it says radical x. If I said ready, set, go, sketch that picture right now, and we had a contest, who would get done first? You've got to have this picture in your mind for next year. Guys, careful. If that says square root of x, don't you agree you can't plug any negatives in for x? So there would be nothing drawn to the left of the origin, would there? Because you're not allowed to use any negative x coordinates. If I plugged in 0, I'd get 0. If I plugged in 1, I'd be right 1, up 1. If I plugged in 4, I'd be right 4 and up 2. If plugged in 9, I'd be right 9 and up 3. that's going to be a slow curve, slowly rising in that direction. Agreed? That's the function radical x. Now the cube root of x, it's going to look very similar to the one I just did. Oh, but it's got a tail going this way. Because think about it, I am allowed to plug numbers that are negative into a cube root function, right? If I plugged in -8, what's the cube root of -8? -2, so I'd be left 8, down 2. Left 1, down 1. 0, 0. Right 1, up 1. Right 8, up 2. So it's a curved picture going through the origin that would look like that as a general thought. If I have 1 over x, you guys agree, if I plug 0 in for x, I'd have a 0 on the bottom, and that's called undefined, and I would have a vertical asymptote going through that point. Remember, any number that creates a 0 on the bottom is where your vertical asymptote is located. And what would happen here, I would end up with a curve sitting up in quadrant 1. And if I started plugging negative numbers in for x, I'd have that same curve, his twin brother, but it would be in quadrant 3. And if I moved over and sketched 1 over x squared, 0 squared still creates a 0 on the bottom, agreed? So I'd still have an asymptote on the y-axis, but I would have that curve in quadrant 1, and his twin brother this time would be right beside him in quadrant 2, because think about it, when I plug negative numbers in for x and I square them, they become positive values. So all my y coordinates have to be above the x-axis. So again, notice what I'm doing. I haven't touched a calculator. We've gotten through 8 functions already, and we're able to make a quick sketch based on our knowledge of these functions and have a general idea what shape we're sketching. So next year, when we look more specifically at these to answer calculus questions, we've already got this library in our mind. That's the goal today. So hang with me. Let's keep going. Next one, y equals absolute value of x. You probably remember that an absolute value function looks like the letter V. So it always has a vertex and looks like a V. Again, this bare-boned basic one, I haven't included any more numbers in here. That's coming later when we look at specifics. I'm going to put a dot on the origin, because you agree if I plugged 0 in for x, I'd get 0 for my y coordinate. And guys, it's going to be not a parabola, but linear in nature and looks like a V. This here might be one that, to be honest, sitting in the math lab the last couple of years, I'm not sure anybody from Mr. DeMarco's class has ever come in and asked me about. Now, this is not an absolute value bar. This is called a greatest integer function. It's called a step function. And we will look at that specifically, I think, on Thursday or maybe next Monday when we get to a specific example of that. But it looks like a set of steps. You're going to start with a dot on the origin, draw a flat step to the end that's 1 inch long and has an open dot on the end of the step. You're going to jump up an inch, draw the same step, jump up an inch, draw the same step, jump up an inch, draw, oh my gosh, and it just goes forever. And it looks like a staircase of steps going in the upward direction because it's a positive value. Again, that one you might not be familiar with. We'll have to look at that specifically here in a few days. If I ever see y equals some number raised to the x power, remember that was called an exponential function because it had a missing exponent. Now notice we've already got a dot here on 0, 1. Why? Because think about it, no matter what this base is, let's say it's a 5. 5 to the 0 power is what? Anything to the 0 power is 1. So no matter what the base is, we know it's going to go through 0, 1. Now what's the shape going to look like? If I plugged in -1 for x, 5 to the negative first would be 1/5, right? So it would be left 1, up 1/5, left 2, up 1/25. But if I plugged in 1, I'd be up 5. You can see what I'm getting at here. We'd have a sketch or a curve that looks very steeply turning uphill like that. And if it's a negative x instead of a to the positive x, think about it. When we plug 0 in for x, we're still going to have a base raised to the 0 power, which is 1. So 0, 1 is still got to be one of our dots no matter what the base is. But now if I had 5 and I plugged in 1, I'd have 5 to the -1, and I would get my 1/5 over on this side and my 1/25 right there, and I'd be left 1 and up 5. So bottom line is, if I have an exponential function, remember, and it's got a negative exponent, it was a decay situation instead of a growth situation, so it went downhill. Wow, we've graphed 12 quick sketches already. 12 quick sketches of 12 basic functions here in our library of mental functions that you've got to have in that brain. If I have e to the x, think about it, is that any different than a to the x? Instead of a being 5 or 3 or 7 or 20, we've got e raised to the x power. So if I plug 0 in for x, anything to the 0 power is still 1, so put a dot on 0, 1. Now guys, remember e is about, do you remember the value? 2.718. 2.718 to the first power would be 2.718. So right 1 and up 2.7 something. If I went left 1, so that was e to the negative first, it would be point something. So this shape is just like the a to the x. And then we use that shape to move into the next one that says ln x. This might be the other one that stumps you on this paper. If I said, quick, sketch that, what's it look like? Guys, the only way to think of this correctly is, remember, go back to Ben. If I ever see a logarithm, my base is understood to be a what one? It's an ln. E raised to the exponent was always on that side of the equal sign, so that would be a y. Equals, and then this number here was on that side. So basically, if I made an XY table right now, I would actually plug -1, 0, and 1. Not in for x, so I'm going to forget that idea. Wouldn't I plug it in for y? Because that's my exponent. Interesting, right? So even if you forget one of these, you can think your way through it real quick. So if I plug a 1 in for y, e to the first would be e. E to the 0 would be 1, and e to the negative first would be 1 over e, which is going to be some decimal. So my graph would be what? Right e and up 1, right 1 and up 0, and then right point something and down 1. So it's still curved in nature, but it ends up using the y-axis as its asymptote instead of the x. And finally, if I said ready, set, go, quick, sketch sine, cosine, and tangent. Remember, the normal sine graph is the one that starts on the origin, right? The period, or the length of sine, is 2 pi. So the halfway point was pi. Remember all that? Halfway between that dot and that dot, we reached a max of 1. And halfway between those two dots, we reached a min of -1. And the sine roller coaster looked like that. Agreed? Cosine is the one that started up on 1, ended at the same height of 1, way down there on 2 pi. Halfway in between at pi, we reached a minimum value of -1. And at the halfway dots on the x-axis, remember, this is not a V, it's curved in shape. It should look as a curved roller coaster like that. That was the normal cosine. And again, tangent, I'm not sure if Mr. DeMarco ever mentioned what a tangent graph looks like. But the reason I've got the bare bones sketch the way it looks here Actually, on a tangent graph, you've got an asymptote at pi over 2, an asymptote at negative pi over 2. There's a dot on the origin. If I went right 45 degrees, which is pi over 4, I'd be up 1. If I went left pi over 4, I'd be down 1. Now, that's not linear in nature because you can't cross the imaginary force field that's there, correct? It's curved up in that direction and curves down in that direction. And looks like that. Wow. Hey, guys, I did not look at a calculator. I did not look at any notes. I calmly thought my way through all 17 of those functions. So as a skilled calculus student next year, you need to have all 17 of these functions in your mental library and quickly have some idea of how to sketch all of them. So when you do start sketching them and working with them, you've got their shapes, their general shapes in mind to move forward into the calculus concepts. Now, there is a note at the bottom. There is one more type of function called a piecewise function, and it consists of any number of pieces of all these kinds combined, and that'll be the last topic of the year that we end the year with at the end of next week, okay? So guys, today we just sat here and sketched our library of functions. Keep this in your notebook. Keep it as you move forward into whatever class you're taking next year. And this will be kind of our reference sheet for the next 2 weeks together. So that tomorrow, on Tuesday, I'm just going to go over 4 specific functions. Like I might have y equals negative 3x plus 7 and do a quick reminder on how to graph a specific linear or a positive and a negative quadratic function. And then maybe our 4th one would be a cubic function and refresh your memory on what to do on those. So bottom line is we'll sketch 4 functions tomorrow. You'll have 4 practice ones for homework. We'll then go to 4 specific questions or functions on Wednesday, and you'll graph 4 of those for homework. They'll be worth 2 points each. Then we'll move on to Thursday and do 4 specific functions that will generally be off this library we just produced, but more specific with some changes and adjustments involved so you can attack and remember how to graph all these as you head into next year. So good news. That was a 20-minute video there. You paid attention. You've got your library all ready to go. There's no homework tonight. I'll see you tomorrow on the 12th, Tuesday the 12th, and we'll start just 4 functions per day. Sometimes it's only going to take us 7 or 8 minutes to do those 4 functions. Sometimes it might take 17 or 18 minutes to do all 4 of them, depending on how easy they are and how many steps are involved. And by the end of next week, you are a function expert as you head into whatever class you take next year, and that'll end our little 2-week ride together here to finish the season, finish the year, okay? All right, great job. Hopefully you've got that all done and sketched and it makes sense. Keep that in your notebook. Have that out as a reference sheet each day, and I will see you guys tomorrow. No homework.